So in this video, we are going to see the magnetic effects of electric current. So first we want to know what is a magnet. Magnet is an object. It attracts small pieces of iron and steel, and when it is suspended freely, it points in the north-south direction. So here, natural magnets or the naturally occurring minerals, okay, they have some magnetic properties and they are of irregular shapes and sizes. So these are called lodestone or magnetite. So these have less property compared to the artificial magnets. These artificial magnets are found later and they are made permanent and strong. So let's see some of the properties of magnet. So these magnets have two poles, the north pole and the south pole. Here the like poles repel each other when they are brought close together, and unlike poles attract each other. So they exist in pairs of poles, and repulsion is only the sure test for testing for a magnet. So let's see what are the magnetic fields and field lines. So magnetic field, okay, it is nothing but it is the region covered around the magnet. So when a magnet is placed, the region around this magnet is the magnetic field. Here, this shows where the force of attraction or repulsion is there. So here it can be detected using a magnetic compass. So let's see next the field lines. The magnetic field lines are nothing but these are the lines around the magnet. So this is the magnet, this is the bar magnet, and here the magnetic field lines are the paths around the magnet. So here this lines starts from the north pole and it comes and flows towards the south pole. Okay, so these lines it can be observed by sprinkling some iron fillings around the magnet. Okay, it can be observed by moving a magnetic compass around the magnet. When it is moved, we can see easily the iron fillings are close to towards the poles because the magnetic power is more at the poles when compared to the center of the magnet. So okay, let's see some of the properties of the magnetic field lines. Okay, this field lines, the first property is it starts from the north pole and merge at the south pole. Okay, then the magnetic field lines are closer at the poles. See, notice, we can notice the lines that are close together at the poles, and these lines do not intersect each other, they will not join with each other. So these are some of the properties of the magnetic field lines. Magnetic field due to current carrying conductor. Here the needle is deflected if a magnetic compass is placed near a conductor carrying current. Okay, so then we'll come to know that the conductor carrying current has a magnetic field around it. So let's consider an experiment. Here there is a cardboard. This paper is filled with some iron fillings above it, and here this is the direction of the current, and here we can see when it is carrying current we can observe some magnetic field around it in concentric circles. Okay, so when the direction of the current is from north to south, okay, the deflection of the needle is towards the east. So likewise, when the direction of the current is from south to north, the deflection, needle deflection is towards the west. So we can explain through this experiment. Right hand thumb rule. So using this rule, we are going to see the direction of the magnetic field around a conductor. Okay, so let's see, this is the conductor. We are holding it with our right hand and the thumb finger. Okay, the thumb finger is pointing towards the direction of the current, and the direction, that is the other fingers wrapped around the conductor, is this direction of the magnetic field. So this is the rule of right hand thumb rule. Magnetic field due to current in circular loop. So when current is passed through a circular conductor, The magnetic field is always in the form of concentric circles, and here towards the center of the arcs it becomes larger, the circle becomes larger and larger and appears as a straight line in the middle. Magnetic field due to current in a solenoid. Solenoid is nothing but it is the circular coil of wires in the shape of a cylinder. So when current flows through this solenoid, it behaves like a bar magnet. Okay, the ends of the solenoid is also behaving like a north and the south poles of the magnets. So here the magnetic field produced by the solenoid is also similar to the bar magnet. Okay, the strength always depends upon the current flowing through it and the number of turns of coil in it. Okay. So next we are going to see the electromagnet. Electromagnet, let's consider an iron nail. Okay, this iron nail is surrounded with a coil of insulated wire. Okay, it is connected to a battery and there is a switch. So let's see, when an electric current is passed through this iron nail, when it is wounded with a wire around it. So this is a piece of soft iron. It behaves like a magnet when current is passed through it. So this magnet is called a electromagnet. Okay. So here the strong magnetic field this inside this solenoid can be used to magnetize this piece of iron when it is placed inside this coil. So this is a called a electromagnet. Force on a conductor carrying current in magnetic field. Here Ampere suggested that if a current carrying conductor produces a magnetic field, it exerts a force on a magnet. Then a magnet should also exert a force on a current carrying conductor. Okay. So here let's see with an example. So if an aluminium rod is suspended horizontally by a wire between the poles of a horseshoe magnet, then current is passed through this wire. Okay, then the aluminium rod is displaced to some extent. Okay, if the direction of the current is reversed, the direction of the displacement is also reversed. So here they say the force exerted is maximum if the conductor is perpendicular, if it is perpendicular to the magnetic field. So the force will be maximum if the conductor is perpendicular to the magnetic field. Fleming's left hand rule. So here we are going to say the direction of motion of a current carrying conductor in a magnetic field is given by this rule, that is the Fleming's left hand rule. Okay, let's consider a left hand. Here the thumb finger, forefinger and middle finger of the left hand are perpendicular to each other such that, okay, the thumb finger always shows the direction of motion of the conductor. This is the direction of force. Okay, here this is the conductor and this will be the direction of motion of the conductor. And here this forefinger, it always points in the direction of the magnetic field, and the middle finger points in the direction of the current. These all fingers are perpendicular to each other. So please note, this is the direction of force, this is the direction of the magnetic field, that is B, and this is the direction of current denoted as I. So let's have with the left hand example. So electromagnetic induction, it is given by Michael Faraday. So here the motion of the magnet with respect to a coil or change in the magnetic field induces a potential difference in the coil and produces some induced current. This induced current is nothing but it is a current produced in a circuit by changing the magnetic field associated with it. Okay, so let's see here, if the magnet is moved towards or away from the coil of wire connected to a galvanometer. Here there is a deflection in the galvanometer needle and this shows the direction of the current. So change in magnetic field produces induced current. Okay, let's consider an example. Okay, here, so take two coils of wires wound around a cylindrical paper roll. Okay, connect one coil to the battery and the other coil to a galvanometer. Okay, so if current is passed through the first coil, if current is passed through the first coil, the galvanometer needle shows a deflection in the second coil. If the current is totally disconnected, the needle moves in the opposite direction. So this shows that the current is induced due to the change in the magnetic field. So next we are going to see the Fleming's right hand rule. Here the direction of the induced current is given by this rule. Okay, so let's consider a right hand, and here the thumb finger, the forefinger and the middle finger all should be held perpendicular to each other. Okay, so here this the thumb finger shows the direction of the motion or the force. Okay, here the forefinger shows the direction of the magnetic field B, and the middle finger shows the direction of the induced current. Direct and alternating current. So here first we are going to see the direct current, that is the DC. So this current that always flows in one direction with time, okay, is called the direct current, and this direct current we get from a battery. Okay, next we are going to see the alternating current, that is the AC. This current, it reverses its direction periodically with the time. Okay, it is called alternating current. So most of the power stations uses this alternating current, this AC current, and it changes the direction every 1/100 second, and its frequency is 50 hertz. Okay, so one advantage of AC over DC is that it can be transmitted over long distances without much loss of energy. Okay. So domestic electric circuit, electric power to homes is supplied through the mains, and this is the distribution box with main switch and fuses. Okay, here the earth wire is a green insulation. It is connected to the metal plate kept inside the ground. So this earth wire, it is mainly used for a safety measure. Okay, particularly for the devices that has a metallic body. It may be a refrigerator, toaster or electric press, anything. Okay, so the metallic body connected to the earth wire provides the low resistance conducting path of the current. Okay, so this helps to not to get some severe electric shocks. So next there are two wires. Okay, one is a live wire with a red insulation. It is a positive wire, and the other is a neutral wire. It is with a black insulation. Okay, the potential difference between these two wires is always 220 volts. Okay, all devices that we used in the domestic electric circuits are joined in parallel, and each device have some equal potential difference. Okay, electric circuit, two separate circuits are used. One is the 15 ampere for the appliances that have high power rating. It may be a geyser, AC, anything else, and 5 ampere for small things like a fan, bulbs, etc. Okay, these appliances are connected in parallel so that every appliances gets equal voltage. Okay, they have different switches for on and off, so the each and other is not at all affected. So next is the electric fuse. It is a safety device. It is used mainly in the electric circuits. It is mainly used to protect the circuit and appliances connected with it from damage due to, it may be due to overloading or short circuit. Okay, and here this fuse wire is made up of metal. Okay, and here it is connected in series with the live wire. So this wire always it has a high resistance and low melting point. So easily when excess current flows through this circuit, the fuse wire melts and it breaks the circuit, and it is mainly meant for safety purpose. So we already know that electric fuse in a circuit prevents damage to the appliances and the circuit due to overloading. So overloading is nothing but it is the condition where there is an excessive high current when it flows through a circuit. So this overflowing can happen for several reasons. It may be due to the increase in voltage, or when the live wire and the neutral wire comes in contact, or if too many appliances are connected to a single socket. So it creates overloading, and it overheats the wires and it can damage the circuit and the appliances connected to that circuit. Okay, next one is the short circuit. This short circuit is caused when the live wire and the neutral wire comes in contact and the current suddenly increases in that circuit. This creates spark or fire or damage to the circuit and the appliances. So these magnets are used in many fields. These magnets are used to find the directions. They are used in computer fields. It can be used for hard disks, tapes and floppies for computers. They are also used for radio and stereo speakers, and they are used in kids toys. They are also used in refrigerators for magnets like that. And magnets are also used to move large metal pieces, and they can also be used for filtering purposes to separate the metallic ores from the crushed rocks. And it is also used in food processing to separate the small metallic pieces that are collected from the grains. Okay, and they are used in medical fields. They are used in MRI machines. Okay, this is used to examine the inner parts of the body, and it is also used to cure the cancer. So these magnets are used in many fields.